Okay, so in this tutorial, we'll go over how to conduct the partial F-test using R and how we could detect multicollinearity using R. So we'll be using the gas mileage data set. Data comes from 32 automobiles, and for this example, I kind of just randomly selected 4 predictors. So right, so it may not be the most obvious choices that I make. This tutorial is just more an example to show how to perform the partial F-test and how to detect multicollinearity, right? So I'm not really using this example to kind of try to solve issues regarding the engineering of vehicles or the scientific reason of gas mileage. So let's just read the data in as usual, and I always like to say just see how the data set looks like, and you can kind of see 32 automobiles with a response variable, the gas mileage, and a number of different predictors, and you can find the description of the predictors in the PDF that's associated with this tutorial. So we're going to just regress the gas mileage against 4 predictors: the displacement, the horsepower, the number of barrels for the carburetor, and the weight of the vehicle. So we're just going to regress it against these 4. And so let's just regress that and look at the results of the ANOVA F-test and the t-test associated with this multiple linear regression model. So first things first, right? The ANOVA F-test tells us whether this model with the 4 predictors is useful in predicting the response, and we notice that the p-value associated with this ANOVA F-test is really small, which means we reject the null hypothesis, and our conclusion is that this model is useful in predicting the response. So that's one thing we take note of. The other thing we could look at is the other results of each of the t-tests for each individual predictor. So a key thing to be aware of is the interpretation. So let's take a look at the last one, for the last predictor, the weight of the vehicle. Now this t-test tests whether the slope for the weight is equal to 0. That's the null hypothesis, and the alternative is saying that the slope is non-zero. Essentially, right, if in this situation we have a pretty large p-value, so we say this is insignificant, so we fail to reject the null. And the interpretation of that failing to reject the null and for this predictor is that, right, when we have the other 3 predictors in the model, we don't need the weight in the model. Now, very often people might misinterpret this and say that, oh, this tells us that weight is not a useful predictor for the gas mileage, and that's incorrect, right? It's not useful when you have the other 3 in the model. And that's how we interpret the results from a t-test for each of the slopes, right? So this is telling us again that this predictor is not useful when x1, x2, and x10 are already in the model, right? On its own, it may be useful. So that's a key thing, a very common misinterpretation. But what we notice over here is that for a lot of these predictors, right, that individually their t-tests are insignificant. So typically that's a sign of multicollinearity, right? Especially if you have an F statistic that is very significant, and yet all the t-tests for each of the slopes, okay, we have one that is significant, but the rest are insignificant. Usually, right, that's a situation when if your t-tests are insignificant but a very significant F statistic, then that's one sign of multicollinearity. So one thing you might consider doing then is, well, could I then drop the last 3 predictors from the model? And you have to carry out a partial F-test, right? Again, individually we know we can drop one of them and keep the others in it, but can we drop these 3? So that's where the partial F-test comes in. So there are actually a couple of approaches in which you can find this using R. So one is to fit the reduced model, i.e. the model with just the first predictor, since we're looking to drop the last 3, and then compare the SSR between our smaller model or the reduced model with the bigger model, right? So that's what I'm going to do. I'm going to just fit this reduced model with just the first predictor, right? Because I want to consider dropping the last 3 predictors, and I use the ANOVA function reduced model with my fuller model, and this gives me the results of the partial F-test, right? So the F statistic for this partial F test, that's the F statistic, and the corresponding p-value for this F statistic is that. So it's a quick reminder, right? The null hypothesis is saying that the slopes for your 3 extra predictors are all equal to 0. That means you can drop them, and the alternative is saying at least one of these predictors has a non-zero slope. So in this case, because our p-value is greater than my significance level, we fail to reject the null, which means, right, we don't have evidence to support the more complicated model, so we'll actually stick with the simpler model in this case. All right, so that's what this partial F test is telling us. Now, another approach, which might look a little bit more complicated, is to actually just use the ANOVA function and apply that ANOVA function to your model with all the predictors in it. The key will be, if you're looking to drop the last 3 predictors, make sure that the predictors that you're considering to drop are listed last in your LM function. Right? So in this case, since I'm looking to drop x2, x6, x10, they are listed as the last predictors, so that's fine. So I could just use this ANOVA function, and this gives me the sequential sum of squares for each of the predictors. So this first sum of squares is the SSR for the first predictor. This sum of squares over here is the SSR for the second predictor, given that the first one's already in the model. So every sum of squares that you see here is the sum of squares for this specific predictor, given that the previous predictors are already in the model, right? So that's how we interpret the sum of squares over here. So how do we carry out the partial F test? Well, the formula associated with the partial F test is we can find the SSR associated with the predictors we want to drop, right? And divide that by the number of predictors. So it's going to be adding up these 3 sum of squares and dividing those 3 by 3, because we're adding the sum of squares for 3 predictors, and then we divide it by the mean square residuals for the model, right? So the mean square residuals can be found over here, 9.62, or you take 259, right? The sum of squares divided by its degree of freedom, you would have gotten that value. So that's the calculation of this F statistic over here, right? Just adding up the sum of squares for the 3 predictors I want to drop, add it up, divide it by the number of predictors, 3 divided by the mean square residual. So that is the F statistic that I could calculate over here. Obviously, it's not as convenient as the previous approach, but this is another way of doing it. And you realize that numerically, these values are very similar. There probably are some rounding off issues. That's why they're not exactly the same. So that's how we could find it using this other approach. And if you want to find the p-value associated with, say, this F statistic, right, we can use this command. So pf gives us the probability, but it gives us a probability that your F distribution is smaller than this F statistic, but what we want is the probability that it's bigger than the F statistic. So we have to subtract that from 1. The degrees of freedom associated with this F statistic, 3, because, right, the numerator degrees of freedom is 3, the number of predictors you're looking to drop, and the denominator is the degrees of freedom associated with the residuals for the full model, right? So if I type this, that gives me the p-value. Again, compare this p-value with the previous approach, pretty much the same. Or if you want critical value, you could use QF, and that gives me a critical value. So if my test statistic is larger than this value, we will reject the null. But in our case, we have a smaller test statistic than that, so we fail to reject. So again, using either the p-value or critical value approach will always lead to the same conclusion. Okay, so that's just how we could perform the partial F test, right, in R. So that's one thing we could do. Another thing that we could do, so we talked about the presence of multicollinearity in this example, right? We think that some of these predictors are correlated with one another. So we have 4 predictors, right? So one way we could do is to compare all the correlations between all possible paths between the 4 predictors. So one way I like to do that is to basically, so this cbind function just means column bind. That means for all the vectors associated with my predictors, I'm going to bind all of them together. So let me just type this, and I'm going to store this inside what I call preds. And if I type that up, right, you see I have 4 columns, each column corresponding to each predictor. Now, if I want to look at all pairwise comparisons, all pairwise correlations, I should say, I just use these correlation functions, COR. And this gives me the correlation. So the diagonals will always be 1, right? Because the correlation of each variable with itself will always be perfectly correlated. But if you look at x1 with, say, x2, that's pretty high. x1 with x6, pretty high as well. x1 with x10 pretty high as well. So we can kind of see, right, since all these values are pretty high, that they are all fairly highly correlated with one another. Another thing we could use to detect multicollinearity will be using variance inflation functions, VIFs. The VIF function actually does not exist in the base R package. So what this means is that you have to load it via another package. So if you actually search the World Wide Web, there are a lot of people who have already written up their VIF functions. We'll be using the VIF function from the Faraway library. So I think we've done this before, but just as a quick reminder, if you want to install a package, right? So every time you want to load a function, you want to load a package, you have to install it first. So once you install it once, you don't have to install it again. But just as a quick reminder, go to install a package, choose the one that's closest to you. So choose the one in North Carolina, and then you can just scroll on this. It's going to be listed in alphabetical order. There are a lot of packages out there that people have already written up. We're looking for Faraway. So whoops. So this, right, and then click on OK. I'm not going to click on OK since I already have it installed. Right, so after you install it, to load a package, we type in library and then the name of the package. And to use the VIF, you just use VIF and put in the linear model inside that function. And it gives us the variance inflation factors for all the predictors. Right, so just a reminder what these values tell us, right? It tells us how much the variance is by what factor the variance is multiplied by, right? When we're comparing between what we have versus a situation when the predictors are perfectly uncorrelated with one another. Right, so typically what we say, right, if you have a very high VIF greater than 10, that's usually an indicator that you do have multicollinearity. So, right, we have 3 that are pretty big. So kind of confirms, right, everything that we've seen so far has led to an indication of multicollinearity. So the last thing I want to talk about is to show actually how you could calculate the VIF, if you didn't have the function. So really, if you want to calculate the VIF for, say, the first predictor, what you could do is to use that first predictor as the response and regress that against the other 3. So I'm going to regress that and store that inside result 2. And take a look at the multiple R square or the R square associated with this regression. If I perform this operation where I take 1 divided by 1 minus the R square of this regression model, the result will be the same as the VIF for this predictor. So let me just run this line of code. 19.8, right? Again, maybe some rounding off issues, but theoretically these values will be the same, right? So basically, right, if it has a high VIF, it tells us that the first predictor is very highly correlated with the remaining 3, right? Because we know what the R square, the interpretation of R square, right, tells us that the this x1, I believe it was the displacement, right? The variation in the first predictor, right? 95% of that variation can be explained by the other 3 predictors, right? So again, they're just all these little things that you could do to get some of these values.